In February of 2017, astronomers wowed the world with the discovery that a total of 7 Earth-sized worlds orbited the faint star known as TRAPPIST-1. Now, a year later, we have learned that they are all rocky planets, and that some of them could potentially have hundreds of times as much water as Earth. But you might wonder, how can we know this about planets we cannot see directly and that orbit an ultra-cool star 40 light-years away that itself is barely bigger than Jupiter? It's possible, due to the very special layout of this system, together with extended observations by NASA's Spitzer Space Telescope, working in conjunction with Kepler, Hubble, and a collection of ground-based observatories. Astronomers can detect planets around stars by carefully watching for tiny, repeating dips in brightness. If orbiting planets are lined up just right, when they pass in front of the star, they block a tiny bit of its light. The amount of dimming gives us the planet's sizes, and the timing tells us about their orbits. This kind of observation has been done for thousands of exoplanets. But to understand what the planets are made of, we need to know their densities, which means we have to measure their masses very accurately. That's incredibly hard, but in the case of TRAPPIST-1, not impossible. If a planet orbits a star in isolation, it's like a perfect stopwatch, with every orbit ticking off an exact period of time. However, adding another nearby planet messes this up a little bit. The mutual gravitational pull between the planets will speed them up or slow them down in different parts of their orbits. The timing is no longer perfect. If we observe the timing variations of the planets over many orbits, astronomers can, using a lot of math, calculate just how much mass each planet must have to create these schedule glitches. It turns out that the TRAPPIST-1 system is ideal for this kind of measurement. The planets are so close together that they have particularly strong gravitational effects on each other that create noticeable variations on the order of a few minutes. Spitzer is particularly sensitive to the infrared glow from ultra-cool dwarf stars like this one. To date, it's devoted over 1,100 hours to accurately measuring the transits and timing for this system alone. Combining that data with a Kepler campaign and ongoing observations from many other telescopes has enabled the most precise measurements of mass and density ever made for a system of exoplanets. So, what does this tell us about the TRAPPIST-1 system? To start, let's see how the rocky planets in our own solar system stack up by size, density, and solar illumination. Now we can add the TRAPPIST-1 planets and compare them. You might first note that while TRAPPIST-1b is a bit on the warm side, C is a pretty close match for Venus in all of these properties. As far as this study goes, they're nearly twins. TRAPPIST-1e is almost the same size and density as Earth, and while it receives a little less illumination, it still gets more than Mars. It's not hard to imagine that, depending on its exact composition, it too could have oceans on its surface. Between them, TRAPPIST-1d has about the same illumination as Earth, but is smaller and less dense. Theories of planetary composition suggest that up to 5% of its mass could be in the form of water, possibly covering it in an ocean vastly deeper than any deep-sea trench found on Earth. The outer planet densities are a little higher, but still low compared to Earth. This could indicate significant amounts of water, probably more in the form of ice as they get colder. Remarkably, we now know more about TRAPPIST-1 than any other planetary system besides our own. And we are still learning more. Hubble has been able to rule out puffy, hydrogen-rich atmospheres around 5 of these planets so far, strengthening the conclusion that they are rocky and potentially rich with water. With the upcoming launch of the James Webb Space Telescope, astronomers will be able to make even more detailed studies of the atmospheric chemistry of worlds like these. NASA's upcoming TESS mission will likely find thousands more systems. And Spitzer will remain a powerful complementary tool for studying small planets around small, cool stars like TRAPPIST-1.